Okay, I hope you can see the slides. Anybody just respond? You can see the
Yes, sir.
slides and hear me? Yeah, okay. So today, let us start on the next topic, which is conditional models. So what we did in the previous set of lectures is that we we tried to model or learn a distribution. Okay, so for example, I have a set of observations, say X about something. Say, let's say the humidity and temperature of a day, and I have such observations of the humidity and temperature, which I call X, over some number of days. And my model here means that I want to find a distribution of X, maybe a Gaussian distribution. I assume some distribution of the likelihood and the prior, and I want to get the parameters of this distribution, the theta of the parameters of the distribution. So let's say the temperature and humidity is a bivariate Gaussian. I would like to estimate the mu and the sigma of the Gaussian. The purpose of this is that two things. First thing is that I want to generate likely temperature and humidity values for a new day, let's say. And I want the second is I want to understand. I want to understand what is the mean temperature, what is the variation of temperature, what are the other distribution parameters. I want to understand them. That's why I modeled them as a distribution. But you call it a one node model because we have only one set of variables X, and I want to find the distribution, and I actually have observations about all the components of X. Say temperature, humidity, two components. I have an observation about all of them. Now let us move on to the two node models, where I have two sets of variable X and Y. Okay, so say for example here temperature and humidity, I can divide anyway. Note that X and Y need not be individual variables, they can be sets of variables. So I have two sets of variables, and I have my past observations about both X and Y. Let's say I have past observations of say both temperature and humidity of a number of days. But for the future observation, it is a partial observation, in the sense that I have only observed the X part, I cannot observe the Y part. So let's say I can observe only the temperature, I don't have an instrument to observe the humidity. And but I'm interested in humidity, I'm interested in the Y part also. So so why I'm calling it a two node model, because I'm dividing the set of variables that describe a system into two parts. One part is the observable X and another part is the unobservable Y. But I'm interested in Y, even though I cannot observe it. So my modeling would involve finding the conditional probability. That means, given that I have observed X, what is the probability that Y takes on certain value? So I want to sort of get an indirect estimate of Y, probabilistically, indirect estimate of Y from my observation about X, about X. So this kind of plate diagram usually you can represent. Also, I mean, well, the moment we say that we want to find out this conditional probability Y given X, we assume that there is some kind of relation between Y and X. There is some kind of causality or relation or dependence between Y and X. So we can represent it by a diagram like this. we observe x, and since there is a relation between y and x, from this conditional probability, I get my value of y. So as you can recognize that this is kind of the supervised learning setting. In the previous examples, I have observations about both y and x, whereas in the new examples, I have observations about only x. If y is real, we would call it a regression problem, and if y is discrete, we would call it a classification problem. But the difference between standard machine learning regression and classification is that we are not just interested in the value of a single value of a y given x, but we are interested in what are the possible values that y can take up given a single value of x. And each of these possible, what are the probabilities of each of these possible values of y given a single value of x? That's what the conditional model finds out. This is in a sense more general, because once you have find out these different probabilities, you can easily convert it into a single value of x. For example, I can maximize this probability and find out the most probable value of y, which is a single value. Note one thing, that this probability theory does all this Bayesian theory just gives you a probability. Maximization is not an part of the probability computation. Maximization is a separate thing. If you want a single value, maximize. There's the other part of machine learning. One part is the finding out the distributions, and the other part is maximizing the distribution to get a single value. That's the optimization part of machine learning. Okay, so we are interested in this conditional probability. There are two general ways of finding this, two general estimation methods of finding this joint probability. One estimation method, called a generative approach, is that we estimate the joint probability of x and y from the past data. We estimate the joint probability of x and y, then apply Bayes rule to get the probability py given x. If theta is the parameter of this joint probability, then basically p of y given x and the parameter theta is p of x given y theta. I missed the p theta. P theta given by divided by p of x given theta. Okay, I missed the p of y given theta. This is the first approach. This is called the generative approach. Why it is called a generative approach? Because you are generating the full distribution x and joint distribution. From that, you are applying the Bayes rule and do it. So that means if you have the full joint distribution, for future examples, you can generate both y as well as x. You can sample from the distribution and get it. The second approach, called a discriminative approach, directly finds out py given x. It is not interested in this joint probability. It finds out y given x, and this py given x, this will be a distribution. The parameters of these distributions are now functions of x. Say this is a normal distribution. Y given x is a normal with parameter f mu and f sigma square. This f mu and f sigma square are themselves function of x. Okay, so we assume we are not interested in how x is distributed. We are just interested in a single value of x. Given a single value of x, we will find f mu and f sigma square, and using that we will find out the distribution of y and maybe find out the most likely value of y. So this second approach is called a discriminative approach. Okay. Note that,
Sir, in the second approach, how are we, like if we are directly assuming a normal distribution, then what is with that we are trying to model?
Yes, see, you tell me, so if we assume a normal distribution, what would be our estimation task? Our estimation task will be finding out the value of f mu. given the data, given some supervised data, XY pairs over the historical XY pairs, my estimation job will be find out F mu x and F sigma square x. That is my estimation job. And this is an assumption. Since all the models we have studied so far are basically parametric models. That means we assume distribution. We assume this is normal. We assume this is beta. Okay, and so this is assumed. This we cannot do anything about this. This we assume. This is a, you can say, flaw of this approach.
Generally, we assume something about the parameters of the model and not or the prior. We don't assume something just about the model itself. Like if we assume that it is a normal distribution itself, then we have, like, even if we are just estimating the parameters of the model, but still it becomes a normal distribution.
Yes, it is still a normal distribution. So no, so what you are see, in all the previous, forget about the two node models, forget about the single node model. So all the cases, you remember, all the likelihood and the priors, the distribution form we assumed.
Yes.
The parameters were unknown.
Yes.
And so we assume two kind of distribution model. One is the likelihood, one is the prior.
Yes.
For the likelihood, the parameters of the model are sort of given from the data. Okay. Whereas for the priors, it is not given from the data. Maybe it depends on some hyperparameters.
Yes.
Okay. So when you get the posterior, which is a product of these two things, then it is a function of the hyperparameters from the prior as well as from the data from the likelihood. And what we are actually interested here is P theta given x, probability of theta. Theta is the parameter given x that we are trying to estimate. And that itself will have a distribution. So see, the function, moment we assume some functional form of the prior, moment we assume some functional form of the likelihood, the functional form of the posterior gets fixed.
Yes, right.
Functional form of the posterior gets fixed. So that is, again, I am saying, see, this whole thing we are studying is a parametric approach. That means we assume the distribution, we estimate its parameter. Whereas there is another big class of approach known as non-parametric approach, which says that don't even assume the distribution. Don't assume that it is normal. Don't all this k nearest neighbor and there are many other things which assume that we do not assume any distribution. It doesn't assume it is a Gaussian or a beta or a gamma.
Yes.
But so far what we have done, we assume the distribution. So there is in the study, there is a big debate. So whether this non-parametric approach is good or the parametric approach is good. As such, you sort of kind of believe that the non-parametric is good. We are not assuming anything. But the problem is empirically it is found out that in many cases, assuming a distribution, then taking a prior and estimating the parameters, they perform as good as not assuming any parameter, because they have their own problem also. If you not assume any distribution, there will be something you need to assume. For example, in k nearest neighbor, you need to assume the value of k and so on. So that also is an uncertainty. Okay, so there is always a debate whether the parametric approach is good or the non-parametric approach is good. For the moment, we are studying parametric approaches. In the later part, maybe one or two topics I'll cover on non-parametrics. Okay, so let us go by parametric approach. That means parametric approach, it simply means that you are assuming a distribution, either of the likelihood or of the prior. And if you assume for likelihood and prior, of course, the posterior gets fixed. Okay, so so the difference between this generative and the discriminative approach is that In the generative, the full joint distribution is estimated, can be recovered, so to say. Whereas in the discriminative approach, the full joint distribution of both x and y cannot be recovered. Only this conditional distribution can be recovered. Note that from the conditional, from the joint distribution, it can get the conditional, but from the conditional, you cannot get back the joint distribution. Okay, you cannot get back the joint distribution. From the joint distribution to conditional is easy, Bayes rule. But the reverse, there is no way of getting it back. So we are losing information about x. We are assuming x to be given, fixed, constant, no variation. And if it is so, then y is now is still uncertain. So if x is fixed, how does y vary or distributed? Okay, so this is the thing. So let us now. So we said that there are two types of this kind of conditional models. One is a regression, where y is real, and one is a classification, where y is a discrete value. So now let us start with the regression problem and exactly see what we'll exactly see is that how does these conditional probabilities, the priors and the functional, how they are computed and what is their interpretation. So let us go to the simple regression model, which is the linear regression model. So all of you have definitely know what is linear regression, but we'll see in a slightly, we'll interpret it in a slightly different way. Okay, so let us see what is linear regression. So what you are given is that you are given a set of these red points where for some particular value of x, the y value is given. Okay, and so this is what you are given. You are given n training examples, supervised training examples, xn and the corresponding yn pairs. This yn is a real value belonging to R. Xn is a vector, is a real vector, capital D dimensional real vector is xn. In the linear regression case, what we assume is that there is a linear relation between x and y. Okay, so what is the linear regression? X is a vector, so we take a weight vector w1 to wd, and we say that yn is a single scalar. So we say yn is w transpose xn, a linear function of xn, plus a noise term which we call epsilon n, a noise term which we call the epsilon n. So wt xn. Note that there is no probabilistic part in this first term. Xn is a given value fixed. Xn is a given value fixed. Wt is also a constant, so there is no probabilistic part in the first part, whereas the noise part is actually a random variable. The noise part is a random variable. The noise part is not only a random variable, it is its distribution is again we assume to be normal. We assume again to be normal with zero mean and some sigma. Instead of writing sigma, we are writing it as beta inverse. So beta is 1 by sigma, inverse of variance. We call it as a precision. We call it as a beta inverse. Okay, initially we'll see later we can change this also. Initially, let us assume that beta is known. That means the sigma of epsilon is known and this mean is 0. You might have noticed one thing, this yn equal to wtxn plus epsilon n, this may also have a plus constant term, plus b term, the intercept. It may also have an intercept. But I am, for ease of visualization, I am initially dropping this because you can always drop this. You can always subtract the mean of yn and you can always make it passing to the origin and always drop it. Actually, all this analysis will not change if we add a b to it. All right. So so let me summarize. So xn is a constant single value. There is no distribution on xn. Wt is a constant vector. Epsilon n is a random variable which is zero mean and beta inverse variance. So it is taking the form as if a normal distribution. So yn is a random variable because it has a non-random part plus a random part. So yn is a random variable. The random part is only epsilon and this part is non-random. So you can I am stating, maybe you can try to visualize, think of it a little bit. So if since epsilon is normal, yn will also be normal. Yn will also be a normal. Okay, because yn is just epsilon plus some constant. Okay, and since this Wtxn is a constant, the variance of yn will just be the variance of epsilon n, which is beta inverse. Okay, and the mean of yn, the mean of epsilon n is 0. The mean of yn will be just Wtxn, this constant part will be the mean of yn. Right. So yn is a random variable which is Gaussian with mean Wtxn and a variance sigma, which is beta inverse. What does this mean? This means if we think of y as some random variables given a particular value of x, so you fix your x, then if you look at the possible y values, it will be a Gaussian distribution like this. It will be a Gaussian distribution like this. And this Gaussian distribution will have mean same as the mean of the noise. So it will, if the mean is less, it will be a small spread around this line. And the mean of y will be nothing but wx, which is this y-axis value, wx. Okay, the point on the regression line, that will be a mean value. So as we go on changing your x, this will be the distribution of y, another x, this will be the distribution of y, another x, this. So the mean of all these distributions will lie on this line, and their sigma will be nothing but the sigma of the noise. Okay, so why is it random? So what we have known is that we have simply observed that y is also a random variable, y is also a Gaussian. This actually we had, if you recall, we had talked about this in the last lecture also. If you fix your, instead of xy, I am calling y2, y1. Actually, I have taken this diagram from the book where it is written like this. So if you fix your y, y1, then your y2 is a normal distribution whose mean and sigma we can easily compute given the linear relation. Okay. And the more the slope of the line changes, or rather the correlation, the epsilon value reduces, this Gaussian changes. So this can easily be observed. Okay, so this is all about the model. The model is very simple, Wtx plus epsilon. And if it is so, then we can straightforward see that this is the distribution of y. All right. So in this so-called linear regression model, so what are the parameters of the model? Parameters of the model you can see is that, let us come back to the expression. Finally, it is this distribution, this called p y given x, y given x that we so much talked about earlier. It is nothing but this normal distribution y given x. What are the parameters of this normal distribution? It is beta inverse, which is sigma, and Wt, and xn. But xn is known. So actually the parameters which are unknown are Wt and beta inverse. So our estimation task or our modeling task here is, given capital N number of training examples, x and y n, you estimate the value of W and beta inverse. In other words, just find the regression line and how much variation around the regression line. That's all you need to find out. If you find out, you have the model. Given x, you can find y. And you can not only find y, you can find the distribution of y. Okay, so simplest, we find out the most likelihood estimate of W and beta. So what we'll actually do is that instead of explicitly finding out W and beta, we'll estimate this conditional distribution, y given W, x and beta. We'll estimate this conditional thing, and we'll see that the conditional will, in some particular cases, will take on a certain functional form, which can be expressed as a distribution again. So that we'll directly find out the distribution, and we'll look at the parameters of the distribution. Those we'll say are the estimated parameters. So let us see. As we use this result, that is Pyn given xn. This is for a single y. Note that this is for a given xn, only given constant value of xn. Yn given xn is normal with WTXN mean and beta inverse variance. So if that is so, and if x1 to xn are independent, then the total probability Py given W and the capital X, which is this training set, is, because they are independent, it is product n equal to 1 to n Py n W x and b. So it is product. And each of these individual yn given xn we have already seen to be normal. We have already derived it to be normal by the properties of random vectors, addition of random vectors and scaling of random vectors. We have seen them to be normal. And so we write this multiplication, and if we complete this multiplication, this product, we'll get this to be this product to be this expression. This expression. This expression is nothing but a n-dimensional multivariate Gaussian. This is the difference. Note that it is a n-dimensional multivariate Gaussian. Okay, where capital N is the number of samples. It is the number of, this is an important, see, now we are sort of, each of x and y, each of yn was a one-dimensional univariate Gaussian. Okay, so moment we do this product and independence thing, this changes to a n-dimensional Gaussian, where n is the number of examples. Okay, so this concept we'll use later in our something called a Gaussian process, which is a very popular algorithm. We'll use it for a Gaussian process. So basically, the product distribution is becomes a multivariate distribution with a much higher dimension, same as the number of examples. Okay, same as the number of examples. All right. So this is the final example. P of y given xb is a multivariate Gaussian where y is a n-dimensional y vectors that we have y1, y2, y3, and n. X is a n cross d feature matrix. So each row is a d-dimensional x vector, and you have x1, x2 up to xn. X is a matrix, right? W is a vector, w1, w2, wd. So the class conditional is a n-variate Gaussian. This is to be noted. It is a n-variate Gaussian. Okay, so you can actually get a very easily a maximum likelihood estimate. What is the maximum likelihood estimate of y? It is the, what is the maximum likelihood? You just maximize this. This is the likelihood. So what you do is that take the derivative, set it to 0. Can you tell what will be the, if we take the, so this is the expression for the distribution. If we maximize this likelihood, so derivative of this with respect to w, if we take and set it to be 0, what would be the value of W? Anybody knows? I'm not writing it out. All of you know it actually. What will be the value of W? Okay, I am giving the expression. You can probably look up and derive it. W will be covariance of xy divided by variance x into variance y. So this exercise you should be familiar now. Moment we know the distribution, you have to get a point estimate, a maximum likelihood point estimate. How do you get the point estimate? From the definition, maximum likelihood. So maximize it. Take the derivative with W, set it to 0, and find out what is W. In this case, if you do it, it will turn out that W is nothing but covariance x comma y by variance x into variance y. All of you know this. This is the mean square estimate. Okay, but we are not satisfied with the point estimate. We are not satisfied with only the likelihood. We are also interested in the prior. We are interested in likelihood into prior. All right. So let us assume some prior. What the prior says, how does the value of W changes? How does the value of W changes? Okay, so W is a let us assume some particular type of prior. What is the prior? We say W is a vector, W1, W2 up to W capital T. We say each of the components of this vector are a normal univariate normal with mean 0 and variance lambda inverse. With mean 0 and variance lambda inverse. And also we assume that not only each of the W components of the W vector are 0, mean and Gaussian, they are independent. These weight components are independent of each other. So the joint distribution of W is the product of these individual distributions, the product of these univariate Gaussians. Okay. So again, if we do this multiplication, you will see that PW is a divariate Gaussian. PW is a divariate Gaussian with this form, lambda by 2. So each of these individual Gaussians are 0 mean and all of them have same variance, lambda inverse. So it is e to the power lambda. Since W is a d-dimensional vector, it is a d-dimensional Gaussian with 0 mean and lambda variance. So if we plot it, it basically means that the most likely, so the W is likely most like it is the zero values of WD are more preferred in the prior, are more preferred. Values, small values or values near zeros are more preferred than larger values. Okay. So see, prior again kind of biases you. It says that these parameter values from my previous experience are more likely. Okay. So in this case, we say that 0 values of WD are more likely. Why we say that we'll see later. It is relation to something called a sparse regression. We can make things slightly different. We assume that each of the weight components W1, W2, WD, they had the same, all of them had 0 mean, they have the same variance, lambda inverse. We can actually change that. We can say that this variance can be lambda 1, lambda 2 up to lambda d. Okay, variance can be lambda 1, lambda d, and this product can, the joint distribution of PW can look like this. Again, independence we still assume of W1, W2, WD, they can look like this, and they have, so you cannot simplify it into a multidimensional Gaussian now, but you have product of a number of distributions. This is slightly, but note the difference between this is that if you assume same prior, the expression is kind of simple. Here it's not a very simple. It's the product of normal distributions, which need not be normal. Okay, so but the advantage is that now if we take this prior and each of the prior they want to be 0, they want to stay close to 0, we can have something called a sparse regression. So if the capital D is very large, we can make most of the WDs to be 0 or their priors to be near 0. Okay, so now that we have this likelihood and this prior, let us now, instead of most likely point estimate, let us now go to the full distribution Bayesian estimate. Okay, so we are, for the moment, we are ignoring any hyperparameter of the prior. We assume that prior does not have any hyperparameter. They are just Gaussians with some lambda. Lambda is not changing. Lambda can change also. That is, the width of this can be a hyperparameter. It can change, but let's assume that's fixed. So thus we have this diagram. So we have xn determining yn by the likelihood, and there is some prior on W, which is knowledge. This is data. In this rectangle is data, and this is knowledge. And the shaded part is kind of a observed thing. Here we observe both in the training data. And this comes to PW, the prior, and this comes to the likelihood. Okay, so let us write down the expression for posterior distribution. Because see, you remember our goal was to estimate W given the training set. What is the training set? Training set is capital X, x1 to xn, and capital Y, y1 to yn. So these are our training sets. These two are given, and maybe some hyperparameters, beta and gamma, and some hyperparameters beta and gamma. Okay, so sorry, beta and lambda. All right, so let's look at the posterior. So the posterior, we apply the Bayes rule, the prior and the likelihood, and I'll work out the posterior, but our steps will be the following. We'll first estimate the posterior, and as we have said, this is a conditional model, so we are interested in y given x. So from the posterior, we are, unlike the previous classes, here we are more interested in the posterior predictive distribution, which is actually the conditional model, so we shift our focus to this posterior predictive distribution because this is a conditional model. Okay, so the posterior predictive distribution, you know, can be derived from the posterior distribution of W by y star given W comma x star. X star will be given to you, it will be observed, beta into p of into the posterior and integrated over. So see, this is another way to look up this is kind of an expectation. So it is the value is y star given W x star b. That is the, you read out from the regression line what is the value of y star. Okay, regression line plus some noise, and this is the probability of that particular W, because see, this value is dependent on, you fix your W, you get a value of this, and the value that of W that you fixed has some probability, which is this. So you weight this value by this probability and add this up over all possible values of W. Over all possible values. We'll soon have a visualization for this. Over all possible values of W. Okay, W can be this, as if you are changing the slope of the line. Each of these are likely from the training set that you have. You can have this line, you can have this line, you can have this line with different probabilities. And this line gives you, given a value of x star, this line gives you this value of y star, this line gives you this value of y star, this line is my final y star as a distribution is the average of these values or expectation of these values, but a weighted average, weighted by the probability of this line, probability of this line, probability of this line, given my training observations, because the probability is coming from the training observations. Okay, so if you assume a Gaussian prior and that linear kind of likelihood, that is Wx plus b, which is epsilon's variance is the variance of y and Wt plus x is the mean of y. If we assume those kind of linear model, and if you assume a Gaussian prior, then again I'm not doing the computation, your posterior will also come out to be Gaussian. So we are also having a kind of a conjugate prior. The prior is, you know that anybody in the exponential family are conjugate to each other. Okay, so we have a conjugate prior. The final expression thus is simple. The final expression is also a Gaussian with mean mu n. Our posterior is also a Gaussian with mean mu n and variance sigma n. Let us look at this comes up after this algebra is done, after these sort of squares and things are computed. Right. So sigma n, the point to be noted is that the posterior is also a Gaussian. The sigma n, look at the expression, is beta times xtx. Beta times this is kind of the variance of x plus lambda. So if x was not a vector, you could have thought of it like that. The variance is beta times x square plus lambda, and an inverse of the whole thing plus lambda. Right. So what does this mean? What is lambda? Lambda is the prior's variance. Okay. And what is beta x? So this beta x is the WT, that factor. Okay, that variance. Right. It is the epsilon, that variance. So these two variances get added. Earlier in the just observation of y, only the beta was there, the noise parts variance. Now it gets multiplied by x and the prior's lambda gets added. Okay. And now I'll explain. Actually, the visualization will help you explain it. This is an important kind of thing. There is a duality. You have the x space and you have the w space. Okay, we are transferring the x space to the w space. And similarly, this is the expression for mu n. Mu n is x transpose x, lambda by beta, identity matrix inverse into x transpose y. Let us look at the way. This you keep in mind, or rather we will get back to it, but let us look at the visualization. Okay, so as I said, there is a dual space. There is a data space and there is a parameter space. Okay, this is a recurring theme that will come up later also. You have a data space and you have a parameter space. So the parameter space is W because it is a parameter of the linear model. Let's say it is two-dimensional, consisting of W0 and W1. So if we plot it, we get the W0 and W1. And since it is two-dimensional, the x value, or rather the xy pair value, let's say, not the x value. So that is also a two-dimensional. That means x is univariate. So this is the data space. That means we basically have our observations in this data space. We have a value of x and the corresponding value of y. Okay. Now let us see how do they transform. So if you pick up any point in this W0 W1 space, it corresponds to a straight line in this data space. Okay, it basically it means that you give a value of x, and from W0 W1 to find a value of y. Change your x, get another value of y. This way get a line. So every point in W0 W1 space is a line in this data space. Okay. Now let us look at a distribution in the parameter space. A distribution in the parameter space. What does a distribution in the parameter space means? A distribution in the parameter space means that some values of the parameter are more likely, which is what we did. Remember, this is what we did in the posterior. This is what we did in the posterior. We find out a probability value for some combination W0 W1. So here we try to visualize it by this color. It means that the center part, these values of W0 W1 are more likely. And the lighter color means they are less likely. Okay, So as if this distribution also you could have plotted it in the data space by saying that some lines are more common than other lines. Okay. All right. So now let us make an observation. Let us have an single observation which is a value of x and a corresponding value of y. Moment you get this single observation, your prior remains the same. Prior, as we have said, remains the same, but the likelihood that's now gets updated. That likelihood is what? Py given x comma w. That gets updated. Moment we get an observation. You remember it is product of normal into normal x1, x2, xn, cap to capsen. So moment you get an observation, your likelihoods get updated. Prior is constant, so posterior gets updated. So this we say earlier it was a kind of everything was equally likely. It is a centered Gaussian. Now this posterior after a single observation gets updated like this. This is the posterior distribution. If we sample from this distribution, this is the sample of lines we'll get. We'll basically get all the lines that are kind of passing through this point. That are not exactly passing with some noise. Take the second observation. Now this posterior gets even further localized. And if we sample from this posterior, you will get a bunch of line which kind of passes close to these both points. If we get n number of observations, this posterior gets exactly localized to a single point. What does this mean? This means the MLE and the distribution, they will collapse to the close to each other. Okay, so asymptotically the MLE, it will converge to the MLE. Okay, it will do, and this is a very attractive say. This is what we want. We don't want a lot of uncertainty about W. We want less uncertainty about W. Okay, and more data you get, the uncertainty gets reduced about what is the possible value of W. Okay, so now let us. So this is the visualization of the posterior. We said that we are not as per se interested in the posterior, but we are rather interested in the predictive distribution. Okay, so posterior we have already derived to be normal mu n sigma n, and the predictive distribution, as we have said, is nothing but integration of this in where you remove the W from this equation. Here remove the W from this equation by integrating. So here again I am not doing the algebra. Your PPD will look something like this. It will still be a normal. Note that this PPD is kind of a slice. It is kind of a slice for a single given value of x star. What is the value of y star? So this thing that we looked up, this is actually a PPD. This is not the posterior. This is the PPD. Posterior is over W. Over. If we drew all your lines, if you drew all your regression lines, that would give you the posterior. Whereas this is the essence of the posterior, the useful part of the posterior, which is the PPD. Okay, so again, this is the expression. It is mu n into x star, and this is the mean, and the variance is beta inverse plus x star sigma n x star. Right. So this is actually a big normal distribution. Since these are conjugate priors, this is still a normal. And you can derive either your MLE estimation or map estimation. Okay, MLE is you maximize the likelihood, map is you maximize the posterior. You can all make these plug-in predictions from this. If you put on these values, but let us look at this full Gaussian distribution of the posterior. Okay, so what is the visualization of that? The visualization of that is something like this. given a value, so what the posterior says, given a value of x, what are the possible values of y? We say that it is a normal, the possible values of y is normally distributed with the mean lying along the regression line, and look at this expression, mean lying along this regression line. Okay, and the variance you see is no longer constant, it is dependent on x star. The variance is dependent on x star. What this means? The variance is changing as you change your x. So the uncertainty, variance is the dispersion, the uncertainty. That spread that is varying as you change your x. Mean stays the same. Mean is it is mu n. So mean, actually this is this. Mean is also changing, but mean is on this line. It is some constant into x. Constant is the slope. So the variance changes. Interesting to note is that the region of x where you have less data has a higher variance. You are less certain about what your y would be. The region where you have more data has less variance. You are more certain about what your y should be. Okay, this approach can, this is we talk about line, we can actually generalize it to nonlinear regression also. Nonlinear regression also, where instead of a wtx plus b, you can have some function fx. One way people handle this kind of nonlinear mapping, those of you who know support vector machine will probably relate, is by an feature mapping. It is a feature mapping, right? So instead of it is a line, so it's still normal. You remember it was wtx plus beta inverse. That was the normal distribution of y. Now it is not wtx plus wt phi x, where phi is a nonlinear mapping, and the beta is the variance of the noise part that remains the same, right? So if you go through, so this is kind of a implicit mapping. So if we go through all this exercise of posterior predictive distribution, your picture will look like this. There will be a possible variation in y along the parts where you don't have data. Okay, so what you can actually do is that you can sort of do an estimate of something. So your nonlinear function can be any of these, with certain probabilities. And all these nonlinear function, one way of interpreting this curve is that they kind of agree on these given data points. They come together on these given data points. They come close in this given data point. So all of these bunch of nonlinear functions, which I am by this envelope I am representing, they all agree or come together in the observations. All of them are constant to agree on them. And after this constant is satisfied, in the rest of the region, they can change, they can vary. Okay, they can be anything with certain probability, of course. Right. So it is kind of a there are, if we look at if you have n data points, it is kind of an n-dimensional distribution where in these points they satisfy, they are constant, they are bound to be same, close to each other, and in the other points they have some degree of freedom, they can change. All right. So this idea has been utilized in something called a Gaussian process, which we will not cover in today's class. Okay, so this is the visualization. So you can have all possible curves to fit this, and you remember from the previous data space to model space mapping, as you have more and more data, all these possible curves, they are now ruled out. Only few curves remain, because you can imagine you have to agree on a lot of points, and this, if lot of points are you have to agree on these observation points, and if the observation points are many, you agree on many points, and finally you try to agree everywhere, almost everywhere. Okay, that's what they are agreeing everywhere, and this is how the posterior predictive would change if you change this thing as you get more and more data, and this would look like this. All right, so with this we okay, all right, quickly, sometimes we have ignored these hyperparameters. We have ignored the beta of the noise part, which is a hyperparameter, which we assume to be known, and we have a lambda of the priors, the spread of the priors, which we also assume to be known. In general, this may not be known. This may be unknown also. So your posterior can be expanded, factorized further. Earlier posterior was assumed lambda beta to be fixed. So this blue part in the posterior Bayesian expression, this blue part was not expanded further. Moment you assume this to be variables, this blue part can be expanded further. Again, a base. This is the first Gaussian. This is the first Bayesian expression. This is the second Bayesian expression. This blue part is the Bayesian within a Bayesian. Okay, so actually, so this I think I am not explaining this, you know. So joint probability of W comma lambda comma B would be W given lambda into P beta into P lambda, and each of these we can. So instead of just assuming now you have a second level prior over beta and lambda. So but the see, so now one thing is becoming clear, that this Bayesian can be expanded. So beta can have a second level hyperparameter. So this can be expanded further. So this P beta can again be expanded as say P beta given beta 1, beta 2, lambda can again be lambda given lambda 1. So you can have many levels of priors, many levels of hyperparameters, and only effect is that this factorization will become larger and larger. So such models are called hierarchical prior models. Hierarchical prior models. Their advantage is that you are assuming less and less about the data. You are assuming less and less about the data, about the parameter. You are moving towards a non-parametric thing. But the disadvantage is that this expression has more and more terms. So unless you have conjugacy in each of these priors. Now earlier conjugacy was between one prior and one posterior. Now you have so many priors. So you have to have conjugacy all over the hierarchical priors. So that is difficult to have. So this expression becomes intractable, and often you require approximations, many kind of approximations to compute this. And the advantage of having more and more hyperparameters, disadvantage of having more and more hyperparameters. Right. So sometimes you have you do something like this. In the lowest level of this prior hierarchy, you have a full Bayesian. And as you go to the higher levels of this prior hierarchy, you go to point estimates to make things simple computationally. Okay, so this general framework can be extended to sparse regression, where you have a sort of prior over the individual components of the weight vector W1, WT, and each of them are close to 0. You have different dispersions for each of them. You can make them as sharp as possible. Okay, so one way of doing is that this lambda d that we talked about, the spread of each of the WD, how much they are spread from 0, they can assume some slightly different prior, a gamma prior with hyperparameters alpha and beta. And the gamma priors, the difference is, forget about this algebra, just look at this, they are sharper. They are a student T, a surfer, unlike a Gaussian. So moment you do that, you can force many of these lambda d's to be 0. That means, suppose you have 1000 x1 to x1000. It is a d-dimensional d equal to 1000. And sparse means because y is dependent only a small subset of these 1000 x's. And this regression, if you have all these crafted priors, you can actually make most of these WDs to be 0, close to 0. And you can work with few non-zero WT. That would be called a sparse regression. There are many methods like lasso and other methods for this sparse regression. But the basic idea is you just play with your prior and force many of them to be 0. Okay, so here I close. This is just an example of conditional model for regression. In the next 1 hour, we'll study a conditional model for classification. First 2-class classification, then multi-class classification. And the whole approach would be the same, but we will do it for classification. Note that this is not the only way regression can be done. You can have many other type of regression. We talked about linear and kernel. There can be general nonlinear. There can be something called a generalized linear models, where you have something called a instead of y equal to wx plus b and ws plus epsilon, you have y equal to fx plus epsilon, where f is called a link function. We'll see that in such a generalized linear model, you can, if you assume any exponential marginal and prior on epsilon and this, then any link function will give you a Gaussian posterior. Any general class of link function will give you such. But I'm not going into that. I just wanted to explain the use of Bayesian statistics for regression. But you can, if you are interested, you can study those generalized regression and the sparse models like lasso and other things. Okay, we quickly take a 5 minutes break. Then we'll come back, and I'm